As Morten mentioned earlier this morning, I'm going to be talking about the performance of what I call the set functions, membership, dyadic iota. But in a broad sense, we're touching on issues that affected version 18.0. So if we cast our minds back to 18.0, there's an assumption that 18.0 was the fastest performing interpreter. But it also introduced some significant bugs. So version 18.2, the latest release, backed out some of those changes and also backed out some of the performance enhancements. So we always had a plan to reintroduce these changes back into the interpreter. How do we do this? Well, very carefully. I presented the start of this analysis last year at the last user meeting. The talk today will be a little bit more systematic and is kind of the conclusion of that talk. Right, so first, what do I mean by set primitives or set related functions? So membership, index of, union unique, intersection without. I'll talk about instrumentation at the end, but also where interval index, unique mask have seen changes from 18.0 to 19.0. And also find, which I also measure but hasn't seen any changes. Right, good. There's going to be a lot of graphs, okay? We're on slide number 5, and I think I end on slide 40, right? So if it gets boring, you're just going to have to pretend you're paying attention, right? Everything will be a membership operation. It'll be a heat map plot. I'll be measuring the total elapsed time for a particular invocation of membership in milliseconds. The x-axis will be the length of the rank 1 array left argument to membership. Y-axis will be much the same, the length of the rank 1 array to the right-hand side of membership. So x and y are for this particular membership operation. 18.0 will always be on the left and 19.0 will be on the right. I'll be talking about 19.0, but everything I present here will roughly translate to 18.2 as well. Last year, I gave a view of different sectors of the input space. Today, I'm only going to be talking about what I regard as the most important sector, which are small or medium-sized arrays. So lengths will only go up to 1,000 or 20,000. Okay, let's begin. I'm glad that Richard mentioned pockets because different inputs interact with pockets in different ways. So we'll go through this very systematically and we'll start off with Boolean values. So again, to reiterate, any particular point on this plot represents, so if we pick a point here on the bottom left, 4,000 elements, membership, an array of 400, an array of length 400, membership, an array of length 200, okay? Boolean values, 18.0 on left, 19.0 on right. For this, profile looks pretty good. Constant time operation, in particular 18.0 around about 2 microseconds. And in 19.0, round about 2.5 microseconds. So 18.0 a little bit faster, but otherwise looks pretty good. If we go out to 20,000 length arrays, so the previous plot would be just a tiny little box here on the left. Again, looks as we would expect. Almost constant time, slight slowdown as we get to larger sized arrays. 18.0, again, slightly faster than 19.0. So 18.0, we're at about 2 to 2.5 microseconds. 19.0, 2.5 to 3 or 4 microseconds. So for Boolean arrays, 18.0, slightly faster. Right, let's go up. Let's go to 1 byte integers. So now we're talking about arrays populated only with integers in the interval 0 to 127. Now, first of all, 18.0, 19.0, there's red all over the place. Fine. Around about similar performance. I don't know if it's going to turn up, if people can see, but on the left of 18.0 here, there's a patch of purple. There's a small array optimization in 18.0, which is not present in 19.0. So that's something where 18.0 has a little bit of a performance gain. But there's a big area of yellow here in the bottom right sector. So here there's a slight performance degradation in 18.0, which we're not seeing in 19.0. If we go out to arrays of size 20,000 now, a little bit clearer, we can see that actually 19.0's performance is better than 18.0's. We see an extension of the issue we saw before. There's a big patch of yellow here. But as I said, 19.0 actually performing better than 18.0. Okay, let's continue. Let's look at unsigned 1-byte integers now. Forget the colors for now because these scales are different. Just look at what the profile. 19.0, nice smooth plot, roughly as you would expect. Things slowing down as your arrays get bigger. 18.0, there seems to be an algorithm selection issue here. So in this sector, some different slower algorithm is kicking in erroneously. If we equalize these scales, you can see broadly performance is the same, except 18.0 has issues that we've seen before and this incorrect algorithm selection that I just mentioned. Right? Let's expand the size of the arrays. Let's go up to 20,000. 18.0, 19.0, roughly broadly matched, besides the issue that I mentioned before. So, if you have 1-byte integers, 19.0 at least as fast as 18.0 was, if not faster. Right, let's continue 2-byte integers. Now values up to 30,000 odd. 19.0, again, nice smooth output. 18.0, I hope this is clear to everyone, it has this banding behavior. Now, I don't want to get too much into the details of what's going on here, but these are being caused by hash collisions. Internally in the interpreter, a table is being created. Every element on the right side of the membership operation is being hashed and is being allocated a position in the table. Where two values are hashed to the same value, that's a collision, there's a clash. The interpreter has to find a new slot for that value to go into. And so if we fix the size of the left-hand left-hand argument to membership, and we just increase now the size of the right-hand argument, so we start here and we go up the table. We start off purple, that's fine, and then it goes to red, okay, the times are increasing, but then there's a jump back to purple again, and this keeps happening. So times increase, then there's a jump back to faster times, and increase, and so on. So what's happening here is, at every one of these boundaries, the internal table size is being increased, so there's not as much collision happening. So that's why this is happening, and it's kind of clearly an issue. So that's in 18.0. 19.0 does not have this issue. Again, scales here are different, so let's equalize the scales and compare performance. 19.0, a lot faster than 18.0. There's yellow all over the place. Let's go to 20,000 sized arrays now. Here, again, scales are different. This one goes up to 0.7, this is 0.07. 19.0, still nice smooth profile. 18.0 still showing the hash collision issue. Let's equalize the scales. So now 0.3 for both of them. 19.0, again, a lot faster actually than 18.0 was, and not exhibiting hash collisions. Right, let's keep going. 2-byte integers. Again, scales are different. Let's just look at what the plots look like. Hash collision issues in 19.0 as well now, but they were present in 18.0 as well. If we equalize the scales, we can see there's a lot more purple for 19.0. So actually, again, 19.0 performing faster than 18.0 was. Go up to 20,000. We can see in 19.0 here at the bottom, so again, the previous plot was just this bottom left corner here. We can see this is an algorithm selection issue. So whatever time we have in this top right corner, in theory, there's no reason why any other value in this plot shouldn't be as fast as that. So we shouldn't be seeing any red or yellow values here. So this is an algorithm selection issue. But again, we're seeing hash collisions in 18.0, and if we equalize these two scales, 19.0 again faster than 18.0, modulo this issue here at the bottom. Right, we'll be done soon, don't worry. 4-byte integers. Scales equal this time, so they both go up to 0.025, 25 microseconds. 19.0 faster than 18.0, hash collisions still occurring. If we go up to 20,000, however, in 19.0, here we see a big difference. So 19.0's performance here slows down quite a lot. We're up to 1 microsecond here, so if you keep an eye on the right-hand graph, we're going to jump from 1 to 10. So you can see here, 10, 15 times the slowdown compared to 18.0 actually. Right, let's continue. Unsigned 4-byte integers. Again, scales here are the same, 0.06 for both of them. Roughly around about equally matched, maybe 18.0 slightly better, hash collision issues for both. If we go up to arrays of length 20,000, however, again, we see the same issue as before. In 19.0, performance degrades as we increase the size of the arrays. And again, if we keep an eye on the scale on the right-hand plot, we go from 2 milliseconds up to 20 milliseconds. So 10, 15 times the performance degradation in 19.0 as compared to 18.0. And finally, we'll look at floating point numbers in the interval 0 to 1. Again, for small arrays, performance between 18 and 19.0 is not too dissimilar. But as we increase the size, we see a performance degradation. Go up to 20,000, again, we see much the same issue. 19.0's performance degrades. Right, okay, hopefully that wasn't too painful. Right, conclusions. What can we conclude from all of this? The first is that if we go think back to what I said at the start of this talk, we had an assumption that 18.0 was blisteringly fast and we had to back out some of that performance. Often, actually, that's not true. 19.0 often has better performance than 18.0. However, there are places where 18.0 is performing significantly faster. We also saw issues where the optimal algorithm between 18.0 and 19.0 still had issues anyway. Right, so what does this mean for you, the end users? Well, first of all, we will be increasing the size of the internal hash tables, and we will be adjusting the algorithm boundaries. So in this plot here, it's 18.0 on left and right. The scales are the same. The only difference is the right-hand graph has twice the size of the internal hash tables, and it's performing a lot faster. On the left-hand plot, we're up to 0.04 milliseconds. On the right, we're down to 0.02. So there's a twice speed up, just increasing the size doubling the size of the hash tables. If you keep your eye on the right-hand graph, we're going to go from double the size and double it again. So now there's purple all over the board, 4 times the hash table size. And we can double again 8 times. Now, it's very difficult to see, so we're going to bring the scales down slightly, and so now it should be a little bit clearer. First of all, profile on the right-hand plot is now a lot smoother. You're not seeing these hash collisions anymore. They're no longer these hash artifacts. So that's one thing that will be changing. Not in version 19.0, as Morten mentioned this morning. We still have to tune these changes and test them thoroughly. But these will be in version 20. We will also be reintroducing where 18.0 is performing particularly well, And we'll also do some code cleanup and some general reorganization, which will have some small benefits. And in the future, perhaps we'll be looking at retained hash tables. I don't know how many people are aware or use these things, and maybe also some slight hash algorithm modifications. That's a little bit more speculative though, but certainly in version 20 you'll see some modifications. Now, I'm glad that both Morten and Richard mentioned workspace full errors. Version 20 will increase the size of the internal hash tables. This will have an effect on workspace memory allocation. So, if that is a concern to anyone in this room, there are 2 I-beams in 18.2 currently, I believe, and certainly will be in 19.0. Now, 8468 will increase the size of the internal hash tables. You can give it a right argument of 3 that will increase the size up to 8. 8469 I haven't really talked about today, but it's a different type of table. It takes a right argument, which is the size of the table in bytes. So this represents 16 megabytes, the max value it can take. Now, do not use these I-beams and think you'll get a performance improvement. You may do, you may not do. If you're worried about workspace memory allocation, then run these 2 I-beams, load your workspace, run it, run your functions, and if everything works, perfect. If you have problems, let me know, okay? And finally, instrumentation. Now, I mentioned at the last user meeting our intention to produce an instrumented version of the interpreter. This is a version of the interpreter that logs certain information that will be useful for me to see. For example, the size of the inputs to these set functions, where in the input space people are using these things. So we now have a version of an instrumented version of 18.2 available for people to use. If you came and saw me last year or since then, come see me again and let me know which version you would like, whether it runs on Windows, Linux, Unicode Classic, whatever. Come and see me, and I'll be very grateful if we could have volunteers so that I can see what sort of data everybody is working with and where to put my efforts. I believe we've got 10 minutes. So in 10 minutes, I'm just going to give you a quick rundown of the instrumented interpreter. Right, so this is 18.2, it's running Linux, it's via RIDE here. It will say instrumented build right there as part of the banner, so you don't get things mixed up. I will run through 8468 I-beam 3. Again, there you go. It will have just increased the size of the internal hash tables. It won't do anything spectacular. Same with 8469. 16 megabytes. Yep, thank you, 8469. Again, it won't do anything spectacular. You can run these 2 I-beams, run your code. If you get workspace full errors and you can't do anything about that, let me know. Instrumentation, that will be 14514 I-beam. You just give it a file where you want to log information to, and as soon as you run that I-beam, it will start logging to the file that you specified. So you can run whatever commands you want. Not that one. Membership IO 25, and yeah, fine, whatever. When you're finished, run 14514 I-beam again with the value 0, and this will write and close the file. Okay, it's important you do that, otherwise if you send me the log file, it won't have things that were buffered but not written out to file. In terms of usage, once the file has been opened and closed, you can also reopen it to append data towards it, so you can do more commands, you can give it more things, yeah, whatever. And if you, whilst one is open, a log file is open, you can give it a second one, and it will write and close the first one and open the second one. So you can run more commands, and then afterwards, don't forget to run 14.540 I-beam 0 to write and close. So it's up to you. You can send me one great big huge log file, or you can segment it up into different ones. Hopefully everything should be fine. The only thing to note is that the folder that the log file that you specify in must exist. So if I type in something like this, it will return an error saying it could not open that file. But that's the only issue. If there are errors, it will return a negative value. It won't spit errors because I want this to be an invisible thing. So, so again, if anyone wants to volunteer, I'll be very, very grateful for instrumentation. And I think that is it. Thank you very much.